MCQs are going to be, coming from the topic that we have covered in the lecture part. So the first question that you have right over here, and we will try to find out the answer together. So the question number 1 is the term atom. The term atom is derived from which Greek word? And I hope you remember that we have covered in that lecture that what Greek word was used for atom and what does it signify? Right? So we are asking that what is that word and what is the significance of that word? We have a couple of options over here. We have A, Atomos, we have Atomio, we have Atmos, we have Atoma. I hope you remember, and I hope you're already been able to identify that correct option, right? So if you're not able to identify that particular word from the series of words, maybe sometimes you forget these Greek words, but I'm sure you remembered that what was the meaning of that particular word. So here we have a couple of options. One, we have meaning invisible. So that is one, invisible. Second one that we have is meaning indivisible. And another one is smallest particle. And then we have unbreakable. So all these options we have. So this is how, sometimes you get confused, although you know the answer, but you are not quite sure that what the exact answer for this question. So if you recall the concept that we have understood, that atom is basically is coming from the word A-tomio, right? This is a Greek word, and where you have A, which is mentioning not, that is the meaning of A, and then tomio is basically to cut. To cut. So not to cut. So you cannot cut this further. You cannot divide this further. You cannot cut it further. You cannot divide it further. So all those options are going to be correct, right? So in ancient Greek philosophy, they were thinkers. Then they postulated that there are atoms that cannot be divided further, and they are the indivisible particles. So from here, the correct option, obviously, if you already recall this, you can easily say, okay, this is the correct option. And at the same time, you have this, which is indivisible. So in this case, correct answer is B, right? So this is how, we can find out the correct answer for these easy kind of questions. All right, let's move on to the next question. All right, we are in the second question, and the question that we have over here is the early Greek philosopher used the word atomio, so that we already know, right? This word represents atom. And they're asking, all right, so what they were trying to represent from this particular word, and it's very, very easy answer now because we have already discussed. So you can really easily, let's go through the options. A unit of energy, all right. Second one, B, a particle that can be endlessly divided, okay. So they're saying you have a particle and you can keep on dividing this particle endlessly. In this third one, the smallest indivisible unit, right, so that cannot be divided further. Next, a particle with positive and negative charge. Okay, positive and negative charge. So at that particular time, during that particular time, the Greek philosophers, they were not able to, identify whether they have positive and negative, because they were able to postulate that atom is the smallest indivisible unit. So I think that we have right over here is the correct answer. And if you have selected that, so congratulations, that means you are able to answer the correct option, which is option C. All right. Let's move to the next question. Okay, so we have another question, and it's also a memory-based question. As you can see over here, the original concept of atom. Again, everything is revolving around the atom, and which proposed as indivisible was proposed by whom? Who was that? Greek philosopher, right? And that basically I haven't covered in my lecture. So right over here, maybe some of you will recall Dalton, because he was working on atom and have theory of atom. So many things were done by Dalton. Maybe you will try to select that option, right? So that is option number 1. Second one, Thomson. Everyone worked on the atoms, but as you see, all of them, most of them, they are more like a scientist, like Dalton, Thomson, Rutherford. But this guy right over here, Democritus, he was the Greek philosopher. He was the Greek philosopher. And, not only just Democritus, along with Leucippus. And Leucippus, I think he was his teacher, and along with him, around 5th century what they propose, that all matter is made up of tiny particle that cannot be divided further. So if question comes like this, whether they are asking about Demodicus, whether they are asking about Leucippus, you should be able to answer those, right? And these are the people who gave the term atomio. Right, so you need to know that, okay, atomio came from these people, and what they believed, basically, they believed that matter cannot be, you cannot divide it further. So you cannot divide them into smaller units, although this is not correct. Now we know that we can divide them further, right? These atoms, they differ in size, shape, arrangement. So they also propose that atom, they can be, you know, different size, different shape, blah, blah, blah. All those things were there. So that was the earlier concept, and it was around 5th century. And so you don't expect too much from 5th century people, but just imagine they were able to identify that there is atom, there is something which is a particle and which is an atom, and it cannot be divided further. And we still are using this term that was coined by them. Okay, all right. So now let's move on to the next one. I'll write the answer of this, which is C. Okay, this is another interesting question. So let's see whether you can answer this before I give you the correct option. Dalton proposed that atoms of a given element are identical in all aspects. So that was Dalton. Dalton was saying that, okay, both of them, you know, these given elements, for example, you have oxygen, you have you know, oxygen, and they both are really identical, same in all aspects. Whether we have carbon, we have nitrogen. That is what he proposed in his theory, and which experimental evidence more strongly contradict this postulate. So what is the evidence that says this is not true, this is not the case, right? I hope you're able to now select the correct option. Let's see what are the options that we have. A, law of multiple proportions. All right. Second one, discovery of a subatomic particle. All right, that doesn't fit. Existence of isotopes, and the fourth one is law of conservation of mass. All right, so I think if you are already able to understand what are isotopes, so you should be able to say, sir, C is the correct option for this. Why? Because isotopes are the atom of the same element having same atomic number. They will have same, okay, let me write down. For example, these are two isotopes, right? They will have same atomic number, right? And what do we mean by atomic number? That means same number of protons, right? They will have same number of proton, but they will have different what? Mass number. So that is very, very important. That means they will have different neutrons. So that is the concept of isotopes. So when we say that, okay, there was existence of isotopes or isotopes, they were identified, that contradicts this particular postulate that you know, elements are identical in all aspects. So the answer in this case is C. Okay, all right, we are in the next question. Let's see what that question is. Which of the following best explains how Dalton atomic theory supports the law of multiple proportions? All right, for that, basically you need to know what is multiple proportion, and we'll do some numerical calculations or numerical type of questions on multiple proportions. But let's see. This is going to tell us which you know, what is the meaning of multiple proportions. Option A: atoms of different elements can vary in size and mass. All right. Second, and this possibly, you know, Dalton is saying that, okay, atoms combine in simple whole number ratio to form compounds. Third, atoms can be subdivided into electrons and protons. Well, that was not known in that particular time, right? We can easily exclude this. The mass of reactants equals to the mass of products. Okay, the story is going into a different direction over here, and you know, multiple proportions. So now when it comes to proportions, since I've already studied those different laws, you need to understand that whenever, you know, atoms, they are going to combine together to form a particular compound. So let's say this is a particular compound. Because they are combining together, there will be a definite proportion. There will be a proportion where the, you know, atoms, they will combine with a simple whole number ratio. Okay, then there will not be a fraction kind of thing. So that is something is being proposed in the law of multiple proportion. So here you can easily see that is the statement that is being mentioned, that they are going to combine, and they will combine in the form of simple whole number ratio. And that is why this option B in this case is correct, because this law says that atoms, they're going to combine in simple whole number ratio to form compounds. Although it's more complicated than that, I have some questions later on that will help you refine your concepts on this particular topic. All right, let's move on to the next question. Okay, so we have another question, which is Dalton assumed atoms, they are indivisible. That is true, considering modern understanding. Now we are comparing Dalton versus, that is old concept of atom versus modern concept of atom, that is new, right? So this is basically what we are doing in this question. So understanding modern, considering modern understanding, which part of his theory remains valid despite of the discovery of subatomic particles. So whenever it comes to subatomic particles inside atom, that is something is new. That should not be related with Dalton. Anything that is related with electron, neutron, proton, that should not be related to Dalton. That's an older concept, and newer concept is this one. Okay, so now we need to understand which concept of Dalton is actually applicable when it comes to the modern understanding of atom. So let's see what are the options we have. I hope that is clear. A, atoms are the smallest possible particles. Okay, that was, we do have more small particles, so I don't think this is correct. Atoms of one element cannot convert it into another one. Okay, that can really happen. So I think that option is also not correct. Chemical reaction involve rearrangement of atoms, not creation or destruction. And then let's see what we have last option. D, all atoms of given elements are identical. No, we have just discussed that. Isotopes, they exist. So that is something which is not in alignment with this option. All right, so we are having this option C, which fits best. Why? Because chemical reaction involve rearrangement of the atom, not creation or destruction. That is what also Dalton proposed, that we need to understand. Whenever there is chemical reaction between different atoms, they're not going to destroyed. They're not going to get destroyed. They're simply going to rearrange themselves and form different compounds. It's just a rearrangement. There will not be creation of new atoms or destruction of the older ones. It's just the rearrangement that is going to happen. So basically, energy is not going to get destroyed. It's going to change its form from one form to the another one. That something like that. All right. So in that case, what we can say is option C is correct, because chemical reactions, they involve rearrangement of atoms, not the creation and the destruction of the atom. All right. So that is correct answer for this. Let's move on to the next one. Okay, so here we have a little bit more complicated scenario for law of multiple proportions. So I think it's very easy to answer this, because we have already discussed the conceptual one. So let's see what it says. Suppose two compounds. We have two compounds of nitrogen and oxygen. Okay, we have nitrogen and oxygen. We have two different compounds. Have mass ratio of oxygen to nitrogen as this. Okay, so we have we can have something like that. And in first case, we have 1.14. It's kind of a little bit numerical problem. And in second case, what we have is 2.28 and this. So there is a proportion of these atoms in that particular, maybe oxide, right? Because it's nitrogen and oxygen. Okay, so I need to correct this, because maybe nitrogen right over here is as 1, and then you have 1.14. That probably is oxygen, and then again 1, and then oxygen in second one is different, which is probably 2.28. Okay, all right. Which law does this data illustrate, and how it is explained by Dalton theory? Okay. All right, let's see option 1, law of constant composition. As I've already told you, this will be the law of multiple proportion, because we have some proportion over here, and let's see whether we can find out that proportion as a whole number or not, because this is important point. It should not be in the fraction. It should be in whole number. That is why maybe it's creating that confusion, it's giving you the values in fractions. But the smallest whole number ratio, that is being told that what is the smallest whole number ratio in this case. All right. Next is law of conservation, law of reciprocal proportion. So that is not the case. So in that case, what we have is we have nitrogen, right? We have oxygen, and we need to find out, because this is constant. We need to find out that what is the proportion for oxygen, because that is the element which is changing. So we have larger mass, which is 28 divided by 1. This is how we're going to identify the ratio. And if you calculate, this is going to come out as 1 is to 2:1, which is 2:1. So that is the simplest whole number ratio, right? So that tells you, this is how you prove it. That tells you that law of multiple proportion where atom combines in the simple whole number ratio to form compounds. So this is how they are forming compound, right? So this is one of the another example that people can ask questions from by using the law of multiple proportion, and you can get some kind of numerical question. I'll also show you some other one. All right, let's move on to the next one. All right, we have the next one. It seems like a little bit complicated, but believe me, they are not that difficult. Okay, in a chemical reaction, you have 4 grams of hydrogen. Okay, we have hydrogen 4 grams. And then 32 grams of oxygen. We have 32 grams, all right, to form water. All right, we are getting water molecule out, right? Okay. When the reaction is performed, only 35.5 grams of water is calculated or collected. Okay, all right. So how much they were expecting? We need to actually calculate that. Let's see mass of reactant. If we try to calculate that, you have hydrogen, which is 4, plus oxygen, in this case 32, and we are expecting 36.0 grams because this is how they're going to combine, right? Because we are taking oxygen as a molecule over here, so I can write O2 over here, not just O, right? Anyway, so that is why we are getting the mass of reactant, and then what actually we are getting is in our question we can see we are getting 35.5 gram, and what could be the reason for that, right? Okay, let's see what are the options we have. What you can conclude about the experiment: A, law of conservation of mass is violated. Okay, usually that is not the case whenever there is a law which is being postulated, so that probably is not the case. Okay, next is some water vapor escaped, law still valid. Okay, C, reaction did not go to its completion. It seems like it got completed because otherwise you're going to have very less of the mass, and they are not going to probably, you'll have only gases. You're not going to get water. So you're seeing that water molecule got collected, so that option is not correct. Hydrogen was in excess and unreacted. I don't think that doesn't make sense because we have a quantified number. So that brings me to the option B. Probably what happened is some water molecules, they escaped as vapor, so law is still valid. So in this case, you can also be asked like this, right? So you have to have that confidence that your understanding is good, and you can understand the chemical reactions also. And sometimes you have chemical reaction, and depending on the temperature, you can have water vapors. They get evaporated, and whatever you are collecting is less. So that can happen in this case. So for me, B is the correct answer. Now let's move on to the next one. Okay, let's see. We have another question over here where 2 samples of carbon dioxide, they were analyzed. So we have 2 samples of CO2, sample 1, S1, S2. I usually write, to get the better understanding of the questions. Now, in first case, what we have 27.3 grams of what? Carbon. In the second case, we have 10.8 grams of what? Carbon. All right. And next is what you have 72.7 grams of oxygen. And another case, you have 28.8 grams of oxygen, right? So that's the combination we are getting. Okay, and do these samples obey the law of the constant composition? Do they follow that? For that, we probably need to find out, the ratio of carbon and oxygen. This is very important. So how we can identify the ratio for sample 1? What we have is carbon. We have then we have oxygen. Let's identify the ratio of oxygen over carbon, right, depending upon the mass they have. Okay, so which is 72.7 divided by 23.3, and that turned out to be, if you calculate, I've already calculated, turns out to be 2.66 around. Okay, let's calculate in case of sample 2, what that ratio is. Usually take, the largest value on the top. We have 28.8 divided by 10.8, and what we get in this case is also around 2.66, right? So as you can see in the both of these cases, they follow the law of constant composition because when we solve this ratio problem, we got the final value which is exactly the same. So in this case, the correct option is the mass ratio of oxygen to carbon is identical. Yes, so that is the correct option over here. We have correct option, which is A. So we'll say yes. So all the options with the no, right, will go. We have two options like this. So in one, yes, because both have the same C ratio by mass, because oxygen always in a higher mass proportion. So that is incorrect. So in this case, A is correct because we have identified that when we solve the ratio, we get the same value. All right, let's move on to the next MCQ. All right, so let's solve this MCQ, which is based on Dalton's atomic theory. The MCQ is, Dalton's atomic theory states that elements combine in simple whole number ratio to form compounds. So this statement is already given, and sometimes you have this statement in questions, sometimes you don't. But we need to understand that Dalton atomic theory says that elements, when they combine to form compounds, they combine in a simple whole number ratio. A sample of 2 oxides of nitrogen is analyzed. So in this case, you have oxide A and the oxide B over here. And we have some values right over here. And this is oxide of nitrogen. So you will have the value of nitrogen and oxygen. And we can summarize this in a very simple way. You have oxide A. In that case, you have nitrogen, which is 14 gram, oxygen, which is 16 gram. You have oxide B, and nitrogen in that case is 14 grams and 32 grams, right? So this is the ratio, the way they are combining and forming these oxides. And now we need to know what Dalton's law of multiple proportions actually say. So the Dalton law of multiple proportions says if 2 elements you have nitrogen and oxygen, in this case, if 2 elements, they combine to form one compound or more than one compound, the different masses of one element that combines with the same mass of other are in the ratio of small whole numbers. So that is basically the Dalton's atomic theory, and that is the law of multiple proportion according to Dalton. So in that case, what we can see over here also, that this is the element that is getting changed, right? Its mass is changed and the mass of the nitrogen is fixed. Now we need to find out the simple whole number ratio. In that case, what we do is we always take the mass of that oxide, which will have a higher mass of that element. So in this case, the higher mass is coming from oxide B. That is very, very important. I'll tell you why. Oxide B and oxide A. So we'll take a ratio like that. If we take ratio like otherwise, for example, oxide A upon B, what answer we're going to get, we'll see that also. But in this case, we'll have oxide B, and we are only taking mass of oxygen, right? So let me write O over here, because that is what being asked in question. We need to find the smallest whole number ratio of oxygen masses. So in this case, we are just focusing on oxygen mass. So as you can see over here, that turns out to be 32 grams divided by 16 grams. And if we solve this, we'll get 2 by 1, and we get the ratio, which is 2:1. Now, if we do otherwise, what will happen? We'll have oxide A upon oxide B, and in that case, the ratio will be 1:2, right? So that answer C will be correct in that case, but actually answer A is correct in this case. Why? Because Dalton's law always says that you need to take the mass of that particular oxide or compound where the element is having highest mass. So this is how you need to calculate. And once you calculate, it should be very, very easy for you, because you already understand the law of multiple proportion, and you should be able to easily calculate the final small whole number ratio. All right, so this is it for this. Let's move on to the next MCQ.